First of all, let me first thank Dan, Chad, and the whole NAE staff who worked so hard to put this show together. Let's give them a big round of applause. So I was asked to talk about energy, but I was also asked to talk about my personal experience during the BP oil spill, and I'll give you a little bit of that if I have time. So first of all, energy. When we talk about energy, it's very important to put that in the context. And there are three issues that we must address. One is that if it's energy, didn't go quite well. Moses, can you help me? I'm pressing the button. Wireless.
Thank you very much.
Okay, all right. Let's see. Let's restart. Reset button. Three things, very important. Because everything depends on energy in terms of the economy, the three securities, extremely important: national security, economic security, environmental security. Now, let's talk about this. Why economic security? We sort of know this. Let me give you some data. If you look at the growth of the GDP per capita, and if you look at the growth of energy use, you can see there's a good correlation. Without the energy, there is no growth of economy. We are back in the medieval ages. So access to affordable energy, extremely important, and so far it's been mostly fossil energy. Now, national security, economic security are generally considered. The environmental part has been more recent. And we all know about global warming. We all know that the average temperature has gone up by 0.8 degrees from the beginning of the Industrial Revolution. But that's the average. Let me talk about the distribution, because I think it's important to note what goes on in the distribution. So environmental security. So I'm going to show you the summer temperatures, the distribution of the summer temperatures. Some summers are hotter, some summers are colder. How does that distribution move? So here's the movie. This is like the horror movie. So watch it. So the red is hot. This is 1950s, 60s. And you'll find an evolution of this distribution, which is a little scary. So the average has moved, certainly, but that's just such a small part of the story. The tail of the distribution, when it reaches 4 or 5 sigma, at probabilities that were unheard of, that has a disproportionate effect on our economy, on our lives, on our livestock, etc. So let's do some accounting. The life of a CO2 molecule in the atmosphere is about 250 years or more. So the CO2 molecules that went up in the atmosphere during the times of James Watt are still there. So how much CO2 have we put in there? So it's the cumulative CO2 emissions since the Industrial Revolution, since it's a big capacitor for CO2, that's about roughly 1 trillion tons in 250 years. If you take all the known reserves of fossil energy, known reserves of fossil fuel, and if you burn it all, if you burn all the fossil fuel known reserves, how much more can we emit? It's about 3 trillion tons. So 3 times more. Then he asked the question, if business as usual, how long will it take to put the 3 trillion tons in the atmosphere? The number of years. It's about 75 to 100 years. So 3 times more in 1/3 the time. That's what we're talking about. Then the economic question comes up, how much is it worth? It's tens of trillions of dollars. So this is the question that is often posed to society. Should we keep our exponential economic growth and ignore the environment? Or should we keep the $10 trillion in the ground to save the environment? And that, my friends, is a false choice, because it does not account for the human mind to engineer things. And that's where we come in. So The best way to explain this is the Stone Age did not come to an end because we ran out of stones. We just found better solutions. So what are those solutions? And are we in a new industrial age right now? Because if the industrial revolution was all about energy, well, we need to create a new industrial revolution. So are there technologies that address all three simultaneously? So we talk about shale. Why is shale so important? Well, this is the map. These are where the shale reserves are. Because we've increased the production of shale gas, the price of gas has separated from the global price of oil. Very important, because the global price of oil fluctuation depends on international events. The domestic price of natural gas does not depend on that. That's economic security. The carbon emissions have gone down because of the shift to natural gas in our electricity sector, and that has brought down the emissions. Finally, if you look at where the security issues are, let's look at our imports of fossil fuel. Where do we import it from? The biggest growth in imports is coming from Canada. Mexico is there, Saudi Arabia is there. Well, there's some recent changes in Mexico which might increase the portion from Mexico compared to Saudi Arabia. And now you have North America as a strategic partnership in terms of energy. Very important. What are the other technologies? I'll give you a few trends. This is the cost of LED in dollars per kilolumens coming down, and within a few years, it is expected it's going to be cost competitive with compact fluorescent lamps. And the growth of the LED uptake is exponentially increasing. Fascinating. Well, what else? The cost of producing electricity from wind is coming down, and the green curve is the growth of wind capacity in gigawatts. So another trend, very similar. The cost is coming down linearly, the adoption is exponential. Solar. The price of solar panels has come down dramatically. In fact, the panel is not the major cost right now, it's the balance of system, and that's over there today, and the uptake is exponential. And in DOE, we created something called the Sunshot program, just like President Kennedy had Moonshot, to go to the moon and come back, return within the decade safely. This is not to go to the sun and return safely. This is to reduce the cost of solar down to $1 a watt, fully install the utility scale, and for residential, down to $1.50 a watt. And that would be the cheapest way to produce electricity, and this is without subsidies. Very important. So we are in these trends of cost coming down and an exponential trend going up. Is this part of the new industrial revolution? Maybe. The other one is storage. These are the cost of lithium-ion batteries coming down. 2008, it was $1,000 a kilowatt hour. Today, it's about $400-something a kilowatt hour, and we can see that. And if it comes to about $200 a kilowatt hour in terms of cost, the car will be cost competitive with gasoline cars with roughly the same range. Amazing. That's what we're seeing. So the electricity system, though, these are components, but the system is very important. And we just heard that the electricity network, the grid, was the greatest engineering achievement of the 20th century. It is the Tesla Edison grid. The architecture is still the same: centralized generation, long-distance transmission, and then distribution. Now that you have all these distributed devices, et cetera, what is the new grid? That's a huge challenge. And in fact, that is the grid 2.0, where you have distributed resources and centralized resources, but they all have to be talking to each other. Information, very important. The other part I'll just say is this is the world. Since we're thinking global now, and where the people are. This is the population density. This is where the lights are. There are about 3 billion people who have no or very limited access to electricity. By 2050, another 2 billion people will be added to the same regions that don't have access to electricity. There will be massive levels of urbanization. The question is, do we extrapolate the 20th century grid for them, or do we create a new grid? And that's something that we should really think about. Finally, I don't know, how much time do I not have?
You got a minute and a half.
Okay, very quickly, biofuels. People think about biofuels as a business. Absolutely, there's an uptake. But if we don't remove CO2 from our atmosphere, we're in pretty big trouble. So I won't go too much into this. I'll talk a little bit about the BP oil spill. And just to give you context out here, this belongs to the Department of Interior. When it happened, the president got the cabinet together and I said, talk to Ken Salazar, this is your, but I have a scientist in my cabinet. That happened to be Steve Chu. And said, Mr. Scientist, Steve, your job is to stop the leak. And so Steve put a team together, small team together, which had National Labs people, amazingly important, very important, the role they played, USGS, and of course, Department of Interior. I shared an office in BP with Marshall McNutt, who was the head of USGS at that time. So what did we go through? There's a beautiful report from National Academies on what it was, why it was caused. And I'm going to give you a little glimpse of what we actually went through. This is what we were trying to do. This is a schematic, beautiful diagram. It's not so pretty down there. It's about a mile deep. And this is a huge blowout preventer where something got jammed, essentially. A tube got jammed out there. And so the question is, there was this big leak, 24/7. It was a ticking time bomb, and we didn't have any data. Let me show you what I mean by that. This is the bottom of the BOP out here. This is the bottom, this is the sea floor. And that's the top of the oil leaking out because the tube had bent, there was a big leak out there, and it was gushing out with methane hydrates. Hydrates are coming out. It's very visible. And he asked the question, in this big BOP, how many sensors were there to measure pressure, temperature, et cetera? And one would have thought there's like hundreds of sensors out there, and we get all the data, and we know exactly what's going on. There was one sensor. There's one pressure sensor right out here. And out of the pressure sensor, this is the reading we were getting. It turns out the pressure sensor had a precision of plus minus 400 psi. And an accuracy, there was an offset, we later on found out, an offset of 900 psi. And this is what we were dealing with, and it was a data-free zone. And we had to make decisions. There was email traffic going back and forth in trying to figure out what was going on and what is inside this thing. And there was, remember, the first thing happened in April 20th when the blowout happened. By end of May, within a month, BP wanted to do a top kill. The mud was being flown through the choke and kill lines. I won't go into the details. And this was the expected behavior, that if it behaves well, the pressure would come down because you put heavy mud, and the pressure would come down, which is good. But if the pressure went up, it's not good. Guess what happened? It was flat. It didn't make any difference. So clearly, we realized that BP didn't know what was going on. No one knew what was going on. So how do you now address this? There were a lot of suggestions. One of the suggestions, in fact, it came out in articles in Science, that maybe we should put a nuke down there and nuke it, and the whole thing would implode, and that'll be the end of it. Luckily, we had some thoughtful minds. So I'll give you one example. This is from Dick Garwood. I don't know if you knew Dick Garwood. He's a member of the Academy. And he sent, by the way, he was the guy who enabled the first hydrogen bomb to be built. He's 80 plus years, the sharpest mind on our team. He's an IBM. So he wrote an email at 2:18 a.m., June 25th. Dear Alex, this is Alex Slocum at MIT, who was part of our team. He said, I hope that I wasn't rude, but this is a topic I know a good deal about. He built a hydrogen bomb. Then he wrote, here are 7 pages of Enrico Fermi's hand from my July 1950 Los Alamos notebook, an early calculation of such containment. This was literally Enrico Fermi deriving the Rankine-Hughes conditions for the elastic shock waves. And he sent that out to everyone. He scanned it and he sent it out. He said, I think it's a bad idea. Just go through this derivation. And I looked at that and I got up a little late because I was also up that night. And here's the email I sent back. Stepping back from all the email traffic, the one below is noteworthy on several accounts and will remain in my memory for a while. I never thought I would encounter a historical connection between the oil spill and Enrico Fermi spanning 60 years. And I'm awed that Dick has his lab notebooks from 60 years ago, and even more so that he remembers where things are in it. And this was going on all the time. And I won't go into the details. There was a new BOP, blowout preventer, that was attached on top of it. There were some, I'll just give you a quick, oh yeah, this is very important. This was a tilt of about 4 degrees, extremely important because the bolts were at almost yield point out there, and we took the risk of it. And then the question is, if you stop this thing, will the pressure build up? And if the pressure did not go up, it was a bad news because there were leaks all over. So let me stop here. I see Ali waiting on me out here, so I'm going to stop here. Thank you very much.